Hello everyone, hope everyone is doing well. Today we are going to learn about regressions. So we will start with a simple regression and then we will look at multiple regressions. Now as the name suggests, regression here means going backwards. So in terms of statistics or in economics or in other social sciences, what we want to do is we want to see if there's a variable. Let's say it can be any variable, something we study in the economy or study in the society. And we want to see, basically, what constitutes this variable. So we are looking for, let's take one example. Let's say that we want to look at the economy. So if I'm looking at average income of a person, so if I'm looking at income, this is the variable I want to study, then I want to know, let's say if I'm a student or someone recently entering the job market or someone who wants to change careers, I want to know what factors affect income. So I want to know, basically, and there are many factors that could affect income. We can list a lot of factors. We know that education does, maybe your experience, maybe experience does. We may have other factors, maybe whether you live in a city or in a rural area, so urban, rural. So your location may affect your income. Maybe it could affect by if you have any specific kind of training that you took, and many other factors. And we could list over on and on and on. Maybe the major you studied, the GPA, and what kind of extracurricular activities did you do? What kind of, and many economists study this, what kind of background did you grow up in? Did you grow up in a rich neighborhood or poor neighborhood? All those can affect our future incomes. So we can list a lot of factors. However, if somebody is asking me, okay, I understand education is important to income, but what is the actual numeric value of the importance of education on income? Or I know experience is important in income, but if I gain 1 year of experience, how is that going to affect my income? So that's what regression helps to find. It helps us to figure out numerically how do these factors affect the factor that we are basically interested to find. So let's use some notations to understand how we study regressions. So we basically work with a equation, a regression equation, which looks like an equation you may have seen in algebra or in calculus. So we have y equals alpha plus beta x plus e. Some people put subscripts. I mean, we may need subscripts later, but for now, let's just use this. So y here is what we would call the dependent variable. This is the variable that we want to figure out. We want to find what factors are affecting this variable. So from the other example that we use income. That is going to be my dependent variable. Alpha and beta, these are parameters. Alpha is what we would call a constant. Beta is what we would call a coefficient. X is what we would call, I'll put it in quotes, independent variables. And we call them independent variables because we believe that these factors since they are affecting the dependent variable, so they must be independent variables. But in effect, there could be other factors that could affect your independent variables. And so I like to use the word regressor for that, but in a lot of statistics books, they use independent variables. So we are going to stick with independent variables. And epsilon here, this E-shaped thing, epsilon, this is what we would call a residual. And so if we are studying income, an independent variable would be education or experience, factors like that. Now, as we said, there are many factors that could affect income. Now, we cannot include every single one of them because there are a lot of factors that could potentially affect income. So the ones that we can't incorporate in it, maybe we haven't collected that data, maybe we don't have access to that data, those are placed in residual. So residual basically includes all the factors not included in regression. So let's say we just included education and experience in our regression. So residual might include the location where you live, maybe the place where you grew up, the trainings you took. So all those things we probably did not include. So those would be in epsilon. Now, if we look at this equation, this looks like a very simple equation. We can actually, if we plot it, let's say we just have one factor. We're talking about just one independent variable, so we're not including two. Let's just say we are looking at how does education affect income. We will start with just one independent variable, and then later we will see how adding more independent variables affect our coefficients and also regression. So if I were to draw a graph, let's say I'm drawing a graph with y and x. So here y is income, x is education. And let's say I take one specific value of education, let's say 12 years of education. 12 years is basically a high school graduate. And then if I spend 4 years in college, I will say I have 16 years of education and so forth. Now, a person with 12 years of education, some people may have income here. If this is income, X is education, and Y is income. Some high school graduates may have a low income. Some may actually have a higher income. Some may have here. So we may see a bunch of incomes around 12 years. So not every high school graduate earns the same income. On the other hand, if I have a 16 years of education, if I have a college degree, I may have another band of education just like that. And this is true for every other level of education. Let's say I just have 14 years of education. Let's say I just studied 2 years of college, then I dropped out. Or after finishing high school, I went to get an associate's degree, which was 2 years long. So that would also have something like this. So if we take all the population, we may have people who has less than 12 years of education, and so we would get other factors like this, and so we would get a scatter plot like this. So we may end up with a scatter plot like this, and we can see that as visually it looks like it as income goes. Well, when income is increasing, education is also increasing. Or, as with scatter plots, we don't know which one is causing what. Is education causing income or income causing education? And that's where an economic model or a theory is very needed that helps us to understand that this is the reason why I think X is education and it is affecting Y, which is income. And so I can see that there's an upward relationship. As we increase education, it seems like income goes up. Now, what regression does is that basically we can't do regression manually by hand because it will be extremely difficult. So we ask a computer program to help us figure out what is going to be a line that best explains all these points. So if I were to draw a line, what would it be that would explain all these points? So now I can see that a line like this is not going to be very helpful to explain these points. Neither is a line like this. So what the program does, a statistical program does, is going to try to fit, and it will be a straight line that will pretty much explain these points. So it's going to tell us what the relationship between X and Y is. So if I'm comparing X and Y with this graph right here, alpha is the constant here, so it's telling me the value of Y when X equals 0. So alpha is basically telling me, so if X equals 0, so which means in this case, if education is 0, I have no education, what is the value of income that I could earn in the market? And as you can see, then if I were to look at one specific value of education, let's say 12 years of education, then the model is telling us, yes, there is a lot of variation of education that we can see, but on an average, or a high school graduate earns some income that the model is predicting. So this value that's on the line and that is basically giving us the y here. We call these values predicted values of y. So we will have a predicted value of y for 14 years of schooling, 16 years of schooling. So basically the points on the line that provides the average value of y. So basically if I go to 16 years of education, this is giving me the average value of income for all 16 years. For everyone with 16 years of education, all this value is going to be called the predicted value of y. So basically, this line, the red line that we drew, is the predicted value of y. And residual, if I look at, again, residual for each individual, let's take one person here. This is one individual that we have who is earning who has 16 years of education, but this person is earning well below the line. Now, this person got 16 years of education, that is in X, but there may be other factors that could affect why this person's education attainment is at 16, but is causing the income to be at a lower level than what the model is predicting. So then this, for that individual, this is what we would call the residual. So for every point, the distance between the point and the line is called the residual. So residual can be positive if it is above the points. So in this case, the residual is positive. And if it is below the point line, the residual is going to be negative. Now, if there is a point that is exactly on the line, for that, the residual equals 0. So a point like this, for this case, the residual, which is E, equals 0. So these are basically the all the things we need to know about regression, at least how to interpret it. But next, we are going to see what is beta. Beta, if this is my line, then beta is going to be the slope of this line. So if you remember from calculus or in algebra, slope was basically equals the rise over run. Since this is a straight line, what we will say is, in my case, the rise is going to be, let's say I'm going from 14 years of schooling to 16 years of schooling. So this is going to be my run. Now, because I increased my schooling by 2 years, how is that going to increase my income? So if I go and look at, let's say, at that income, when my education attainment is 14, I am earning a certain value of income. Now, when I move to 16, I end up earning another value of income. So this run is leading to this rise. We are then going to find what is the value of this rise. So this is the green part, and then divided by the value of that run. And so this is what beta is going to equal to. And finally, when we are using Greek letters, we are talking about the population. So the population parameters are telling us if I had access to everybody's income and everybody's education attainment and I ran the regression, this is what I would find. Now, as we have been talking about in statistics, it is very difficult to find the population estimates. So what we end up doing is basically then, since we don't have access to the population, we have to estimate the population parameters using a sample. So we then get a sample of the whole population. We may do a survey or we may get data from the government, and where we have basically different individuals and we collect their income and their education. And then what we do is, from this sample, we run a regression. So we normally, if it is a sample we're running, we are going to use A plus BX plus E, where these are telling us, these are parameters. So the alpha or A and B that we have are parameters that we obtain from the sample. And we are going to use these parameters to basically find what is alpha and beta, which are population parameters. Now, there are certain things we have to assume before we run regressions. One is these parameters, alpha and beta, we assume these are linear, which means that they are in this shape. We cannot estimate y equals to alpha squared plus square root of beta x plus epsilon. So we don't know, we cannot do things like this, or we cannot estimate alpha square over beta divided by beta over alpha cube. We cannot estimate things like that. Alpha and beta have to be linear. We also put some restrictions on the residual. We say that the residual has a mean of 0. So if I added all the residuals of all these individuals, and that would add up to 0, which means some are positive residuals, some are negative residuals, and so the average would be 0. And the variance of each residual at each point is going to be constant, which means that, let's say if I go back to my original data here, it is a little messy, but if you notice that here what we did, then the values are within a certain border like this. So my points all vary between, no matter what education it is, it varies within a certain band. And so this tells us that if this is the mean, and the average is basically the regression line, then the variance or the spread of the points are basically going to be the same no matter at what level of education we are at. Now, that is not usually the case. In many cases, we will see that the points are all over the place. So it could be that we may have something like this where, at different values of x, we see that the spread is different. So the variance changes of the spread changes as we change x. Now, this is what we will say the variance is not constant. If this is the case, then we may not be able to use a regression like this to estimate our parameters. We have to use something else. And there are specific regressions for that, but it's beyond the scope of this lecture. So we are going to study it. If you want to study it later, we can study it later. So we assume that the mean is 0 and there is constant variance of the residual. And we also believe that if there are more x's, the x's are independent of each other. So basically, we may have other x's. So in this one, we just included education. We may have experience and others. Basically, those variables don't affect each other. So basically, they all affect income. But if I had another one, let's say experience that I collected and that I added in this regression, experience and education don't affect each other. But experience affects income and education affects income. And again, if there are cases where education and experience are affecting each other, let's say, then there are other regression methods that could be used to mitigate that problem. So this is all we have for now, and let us now look at an example. How do we run regressions? So this is the data set I just generated. Now, we would like to see how does education affect income, and then in a later one, we will see how does experience and education together affect income, and then how does living in an urban area affect income. And this 1, 0 variable is called a dummy variable, and we are going to see how do we interpret that. So let's start with just education, income and education, and see how this works. So what I will do is I will go up in this ribbon and then I'll click on data. When I go to data, there is something called data analysis. So I'll click on that. And then down here, I'll click on regression and I'll click OK. Then it's asking me what is my y range. Y is my dependent variable. So I'm going to select income to be my dependent variable, and I will highlight all the income. Notice that I selected the name of the variable too. And my x, I will select it to be education. And then I will say my value has labels. I don't want the constant to be 0. My confidence level, I wanted a 95%, and let's say I wanted let's just put it right here. And down here, there are other things we can get. Let's just say we want residuals, and let's say we want line fits. We can also add for residual plots, and let's just add those three. And then we click OK. And finally, we get our output. Now a bunch of numbers popped up, so what we are going to do is go one by one to explain what each of these numbers mean. So the first thing is there are 40 observations. So that is something that we need to know. Let's say that you have collected 200 observations, and now in your sample you have 200, but the observations counts as 40. That's a problem, so you probably need to go back to check what is going on. Now in this case, let's say we have our variables down here. So we have something called ANOVA here. ANOVA is the analysis of variance. This will be a little more important when we have more variables in, so I'm going to wait before I talk about this. Then we have something called R-squared and adjusted R-squared. So adjusted R-squared, this is telling us, actually R-squared and adjusted R-squared, they tell us very similar things, but we're going to use adjusted R-squared. What adjusted R-squared tells us is, so adjusted R-squared is telling us what proportion of the dependent variable is affected by the known factor. So X, which is, in our case, education. So this R-squared is telling us that education only affects about 0.9% of the variation in income. And so we can write that here. And needless to say, since I wrote it this way, R-squared is something that ranges between 0 and 1. So the larger the R-squared, the better it is. But if the R-squared is, let's say, 100%, that's not really good, which means that the education and income are absolutely almost the same thing. Now, why did we use adjusted R-squared and not R-squared? We could have used R-squared, which is fine. But what R-squared does is that, supposing here we see that education is only affecting if I look at R-squared, it's only affecting 3.4% of the variation in income. Then what I can do is, if I kept on adding more variables, and even if variables that are nonsensical, let's say the hours of sunshine in a given day, or let's say the maximum temperature in July, does that affect income? I could add many other variables that may not really affect income. And if I kept on adding those, R-squared would go up. And the way it is constructed, that makes R-squared go up. So, but adjusted R-squared, it kind of takes into account that if you add more variables in, that is probably not going to increase the R-squared. So it adjusts for the increasing number of x's that we add in our regression. Now, down here, we can see the coefficient, and the intercept is called is 1792, and education's coefficient is 13.68. So if I were to write this in our equation form, I could write it as in this form, y, or I could also write it as income. So basically my income is going to be equal to 17.92.31, which is going to be my intercept. And the coefficient on education is 13.68 times education plus E, which is our residual. So these numbers, we plug it in here. This is the standard error of the coefficient, which is telling us what is the spread of each of these variables. Now we were going to talk about that in a little bit. Now let's look at how we can interpret these coefficients from this equation right here. Let's take two individuals. And so let's say we randomly pick two individuals who have, let's say, the same, everything is the same. So all the factors that go in E that we haven't included, let's say experience and all that. So we can say all factors are equal except for education. So maybe one person has, let's say person 1 has 12 years of education and person 2 has 13 years of education. So one has 1 extra year of education, but every other factor, the same amount of experience, the same amount of training, and all, they grow up in the same neighborhood, every other factor is the same. So what that's telling us is that everything in epsilon is going to be the same for them. So let's plug them in and see what does that mean. So if the person has 12 years of schooling, how can I find out what income they have? So I can plug in 12 in education and see what will that equal to. So I can say that predict, or the model can predict the income of, so the model can make some assumptions on the income of person 1 and person 2. So if the person 1, first person, has 12 years of schooling, then I can plug in that and I can say it will be equal to. So I will get something like this for person 1. You make this a little bigger. The income, or the predicted value of income, is going to be that 1792.31 plus 13.68 times 12 plus E. We can put some number for E. Let's just say we give a value of E equals 10. Now we said this person 2 has the same history as person 1. So everything else is the same. Just person 2 has 1 additional year of schooling. How is their income going to be different? So now if I do person 2 minus person 2's income minus person 1's income, this is what the model predicted for them. So now if I want to see how is person 2's income different from person 1's income if person 2 has 1 additional year of schooling. So in that case, I can take person 2's income, which is here, and I'm subtracting person 1's income. So basically, I'm taking the predicted income of person 2, and I'm going to subtract person 1's income from that. So if you notice here, this income right here, this is person 2's income that we got from here, and person 1's income is this number, which we got from here. And now if you solve it out, and if you see how, if you want to see how it works out, you can do the algebra and work on it. But one thing you will notice is that the intercept falls out, the values of the residuals fall out. So all that is left over is going to be just this part. So 13.68 minus 13 minus 13.68 times 12. So we have this amount left over. Now if I solve this out, you can see that all that is left over is going to be 13.68. So then I could do all these steps again for each variable, but what I can see is if I increase education by 1 unit, y goes up by 13.68 units. And that is what the coefficient is in this case. So I can write out, in our case, and this is true in regression, if education is in this form, then if it goes up by 1 unit, income will go up by the magnitude of the coefficient. So that's an easy way of finding it out. Now, the other thing we downloaded is the residual output. We have all these things down here. Now, we have a column called predicted income and residual. Now, what is predicted income? If I go up here, I can see that for 11 years of education, my income is 2120. So what I can do is I can actually, since this is my intercept, this is the coefficient on education, I can go and if I were to predict, it is equal to intercept plus then the coefficient on education, which is 13.68 times the value of education that we have, which is 11. And I get something called 19.42. So what this number is basically, it is equal to 1792. I'm not going to write all the decimals. So this is, since I plugged in the value of education to find out what exactly could be the value of income, this is what we call the predicted value of y, or the average value of y. So if this is the education attainment, this is what I predict that the education or the income that will arise from this level of education. But the actual income, which is what we have here, is 2120. The difference between these two numbers is the residual. So the residual is going to be value of income minus the predicted value of y. So this is the value for the first individual, and we can calculate the predicted value of y for the second one, for the third one, and so forth. But we can also look at this right here, and we can see that Excel does it for us. So after copying and pasting the variables here, we can see that for the first line, my predicted value of y was 19, that I calculated was 19.42.869, and the predicted value that Excel gave me is the same. And the residual is that value. Now for the second one, as we can see, the predicted value is 1915, but the actual value is 1679. So the person is earning less than what the model is telling us. So in that case, we see that the residual is negative. And then we can also plot the residual as we see. So here we have how education and income are going. So we have, this is what education and income, what they are looking at, and this is the predicted value. We can also see how education and the residuals are looking like. So in this case, we can see that, well, I mean, the educations are kind of within the same band. So we can say that, yes, since the education and the residuals, when plotted with education, they are not all over the place. So that seems like there may not be any issues with like changing variance as we increase education. So we can use this regression for other analysis. Now let's say we wanted to, so we have done our simple regression, which is just one independent variable and one dependent variable. Let's say we want to add more dependent variables in our regression. So now what we will do is called a multiple regression. So let me delete all this. Multiple regression means that there is more than one dependent variable in the regression. Let's say we want to include education and experience in our regression to see how do these two variables affect income. So to run the regression, multiple regression, we go to, again, data and go to data analysis. We select regression, and then for my y variable, I will select income. That is my dependent variable. And then for x, I will have education and experience. So I will select those two columns. And then I will include labels, and I want my output here. Let me keep the residuals, residual plots, and line fit plots, and I'll click OK. Now let's look at our variables. We included two variables in x variables, so we have two independent variables. Now if I look at my adjusted R squared, it is 10.5%. So we can say 10.5% of the variation in y is due to education and experience. So the rest 89.5% is not known. We don't know what exactly is that. That's in the residual. But 10.5% is due to education and experience. Now let's look at this ANOVA table. ANOVA here is telling us we are doing a test basically where the null hypothesis, we're doing the hypothesis that in the null hypothesis is all the coefficients that we included equal to 0. And the alternate is that at least one of the coefficient is not equal to 0. So here we can look at the significance of f, the p-value, which is to tell us whether we reject the null or not. So we can look at this value, and if we are testing at 5%, so we can see that the p-value is less than 0.05. So we reject the null. Because the significance is less than 0.05, we can reject the null. We can also find the critical value of f and compare it with the f-stat here, but it's already given to us, the p-value, so we can just use the p-value to find that. What this is telling us is that if I were to run a huge regression, then if all the coefficients were basically statistically no different from 0, then this p-value would have been very high. And so it would, even before I go into looking at the coefficients, I could look at this p-value and say that, well, this regression is no good. But if the p-value is less than 0.05, I can go that, okay, at least some of the coefficients are not 0. There are some non-zero coefficients, and so we can look at the results to see how those variables are affecting the dependent variable. So let's go down here. We can again write our equation in the form of we have our coefficients here. We can write in front of like this in terms of an equation. So we can say, so here we see that income is a function of 1665.195 plus 16.52 times education plus 19.85 times experience plus E, which is the residual. And so again, if we plug in our variables here, if we plug in whatever the first number is, so if I plug in 11 in education and 8 in experience, I should get this value, the predicted value of income right here. So in this case, how are we going to interpret education and experience? We can do it the same way. We will say, but here now we have to add something else. Remember when we were looking at a simple regression, we said that everything else in the residual was the same for those two individuals. So if we have person 1 and person 2, they both had the same level of everything. So everything in the residual is the same, except one had one additional year of education than the other one. Here we will say the same thing. We'll say they both have the same residual and the same years of experience. And we can pick a number. So we can say, let's say person 1 has 12 years of education and person 2 has 13 years of education. But they both have, let's say, 10 years of experience, and let's just put a value for residual, 20 residual. So if that were the case, if we plug in for person 1 and person 2, we can see for person 1, the value will be, so this will be the value for person 1. For person 2, we will get the same equation, except that instead of 12, we will have 13 years of education. So now if I found the difference in income for person 2 minus income of person 1, we will see that everything else basically cancels out. The only thing that's left over is the coefficient on education. So when we write this up here again, this part, the first part is from person 2. So this part is from person 2, and this part that we have is from person 1. So we are subtracting person 2's income and person 1's income. And then when we do that, if we solve for it, we will see that what's left over is going to be 16.52, which is the coefficient on education. Then what we will write, if I were to just look at how to interpret this, we will say, holding all else constant. So holding all else constant, an increase in education by 1 year will increase income by $16.52. We can also do the same thing with their experience. You can do the same exercise, but we can say, so we will say holding all else constant, an increase in experience by 1 year will increase income by 19.85. And that's how the coefficients can be interpreted. So holding all else constant says that everything else of the two people are the same, just we are increasing experience by 1 year. And so that helps us talk about the coefficients. Now, what about something like dummy variable? How do we interpret that? So let's say I want to run only education and urban. I cannot put, the way Excel does it, I have to put them next to each other. So if I want to run this regression now, where the dependent variable or the independent variable is education and urban, I have to put them next to each other. So let me run this regression now. So I will say, again, I go to data analysis. regressions. My y is already picked. X is, I'm going to pick it again. And let me put this in a different worksheet. Would be easier. And I click OK, and I get these numbers. So here again, I find my variables here. Again, I can see that education and urban together affects y, or affects 89.9% of the variation in y. So we can easily interpret our variable education the same way as before. What about urban? How do we interpret urban? Urban equals 1 means if urban equals 1, so we may encounter variables like this, and we call them qualitative data, and we normally show qualitative data in terms of dummy variables. So urban here is what we call a dummy variable. A dummy variable is something that just takes two values, a 0 and a 1. If it's 0, it means something. If it's 1, it means something else. So in our case, we code it in such a way so that if it's equal to 1, it means the person lives in a city. If urban is 0, it means the person lives in a rural area. So we can use other variables as examples of a dummy variable. Maybe in our case, maybe it may be car brands. So if a car, let's say we had something where we were looking at what cars people buy, maybe a dummy variable, maybe a car is Toyota versus not Toyota, or Honda versus not Honda. As we just saw, location is that. We may look at race or ethnicity. We may code it as a dummy variable. So if person identifies as white or as African American or as Asian, they can be coded as such. So white versus non-white, let's say Asian versus non-Asian. So how do we interpret those coefficients? So since we just have two variables in, we can do the same exercise as before. So I can say, holding all else constant, I can plug in variables like that. So I can say y equals to 1613.97. So I wrote down the equation as such, and now I can say holding all else constant. So basically everything else is the same. Education is the same value, except that maybe person 1 lives in urban area and person 2 lives in rural area. So maybe we are, and now we are saying we're holding everything else constant. Just person 1 lives in an urban area, so person 1 will get urban equal 1, and person 2 will get urban equal 0. So if I plug that in for person 1, and again, let's just add some variable or some value for education and residual. Let's say education is 10 and residual is 20, and urban equal 1. And so for person 2, we have everything else the same, just urban equal 0. So now if I find the difference in income between person 1 and person 2, then if you solve it out, what will be left over, everything else will get canceled out except for the coefficient of the urban dummy, which would be, we would get this much left over. So the way we would interpret it is saying holding all else constant. So we will say holding all else constant, a person living in an urban area or in urban areas earn $303.71 more than a person living in a rural area. So that's how we interpret our coefficients. Now, what about all these other numbers? What are these for? These numbers help us in hypothesis testing. So let us now work on hypothesis testing. Supposing I want to find, does education affect earnings? And this is my question. And so my null is there is no effect of education on earnings. So basically you can study as much as you want. There's nothing happening to your earnings. So education does nothing to earnings. And the alternative is there is some impact. So using what I have here, if you look at the coefficient here of education, if this coefficient were equal to 0, then if I were to plug it right at here, instead of 13.36, it would be just 0. Then if the coefficient is 0, no matter what I multiply with 0, y would always have no effect by the magnitude of education. So another way of writing that is going to be, so instead of writing it this way, I can write it as my null is beta equals 0, where, so I can say beta is the coefficient on education, and my null is going to be that beta equals 0, and the alternate is beta is not equal to 0. So beta could be negative or positive. And so if beta is positive, education has a positive effect on earnings. If beta is negative, then education has a negative effect on earnings. Now notice we are not, previously we said beta was for the population, but what we are estimating is B, as we said. But when we are testing for hypothesis, we are not going to test the samples coefficients. We are actually testing it for the population. So that's why we're writing beta. So after writing that, we found out our coefficients, and then we have our standard error. So we are testing again, if you notice, whether beta equals 0 or not equal to 0. So this is our value of our coefficient. This is B. So we are testing, our t-stat is going to be just B, whatever we found, minus 0, since we're testing whether beta is equal to 0, divided by S over square root of n. S bar, I tried to write a bar there. But this value is what we call the standard error. So if this is the standard error, and B minus 0 is basically B, so basically then our t-stat is going to be equal to the coefficient B divided by the standard error, which is my standard deviation divided by the square root of n. So basically, if we know the B, and we know our standard error, so B divided by the standard error will give us this t-stat. So if I look at this number here, 13.36, this is my standard error. If I find the coefficient divided by the standard error, I get 3.573, which is exactly the t-stat. So this is my t-stat. Now I want to find the critical value of t. If I were to find what it is, let's say I'm doing it at 95%, which I would do t.inv 0.05 divided by 2, and degrees of freedom would be, I have 40 minus the number of x variables I have, which is 2, minus 1. The 1 is for the constant or the intercept. So I'm going to, since it's a two-tailed test, this is my t-value. This is for the left side, so the right side would be positive 2.02. And so I will compare my t-stat with that. And I find that my t-stat is much higher than the absolute value of this. Let me just put a negative side in front, so I get that. I can also find the p-value of this t-stat, which would be, this is on the right side. Again, if I draw it just for a recap, so my 3.58 is here. So I need to find the area of this to the right, and then also the area of this to the left. So what I need to do is find equals to 1 minus t dot dist. Then the t-stat is going to be this value, comma, the degrees of freedom is 40 minus the number of variables I have, which is, or x variables I have, which is 2. I have education and urban, or minus 1 after that, which is the intercept that I have, comma, true. And then I close the parenthesis, and then I multiply that by 2. And I get a number, 0.001002, which is exactly this p-value. However, one caveat here. Here we have the t-stat to be positive. That's why we use the, we said it was near in the positive side of the t-distribution. Now, if the coefficient was negative, the t-stat would have been negative, then we wouldn't need to do the 1 minus thing for finding the p-value. We would just do 2 times t dot dist, and then we would write the t-value that we have, which would be negative here, the degrees of freedom, and then cumulative, we would say true, and then press enter. So all the numbers are given to you. You don't have to calculate any one of these. And I also get a confidence interval of the coefficient. So if I were to find, basically if I have the coefficient plus minus the t critical value, which I actually had 2.02, times the standard error, which is this number, I would get the lower and upper 95%. So it's telling me that the average coefficient of education is 13.36, but it could range between 5.78 to 20.9. So then if I were to do this test, I can see that after I run the regression, I look at education, the coefficient is 13.36, the t-stat is that, p-value is less than 0.05 since I'm doing it at 95%. So we can say then, holding all else constant, a 1 unit increase in education increases income by 13.36. This part we have done before, and this value is significant at alpha equals to 0.05. We can also write that because p value is less than 0.05 or the t-stat is greater than the critical value of t, but we don't need to do all that. This statement is enough. We can also do the same thing with, let's say we were doing a hypothesis testing on urban. We can say, is beta equal to 0 versus not equal to 0, where beta is the coefficient on urban. I can see the standard error is 16.58. The t-stat is 18, which is very high compared to what the critical value of t is. To find the critical value of t, we would do t dot inv. The probability is 0.05 divided by 2, or let's just write alpha divided by 2. The degrees of freedom would be n, the number of observations we have, minus the number of x variables. So the number of independent variables we have, minus 1. And that would give us the critical value of t. So we can find that and we can say the t-stat is greater than the critical value of t, or we can just look at the p-value and say that, well, the p-value is less than 0.05. So holding all else constant, a person living in an urban area earns this much more, and it is significant at the 5% critical value, which also means significant at alpha equals 5%. So we can say, so we reject the null. And we can do it with all the other variables. We can see that we can add more variables in and see how the coefficient changes. So that's a different thing. That's a whole different chapter. But for now, this should be good about the introduction to regression. So hopefully this was beneficial, and I will see you at a later video. Have a good day.